So we are starting with next chapter, which is wastewater characteristics. The first question is the relationship between oxygen consumption and equivalent biodegradable organic removal, that means BOD, in a closed container with respect to time is shown in the figure. So with respect to time, oxygen consumption and equivalent organic removal. See, this is the line of BOD exerted and this is the line of BOD remaining. Okay, assume that the rate of oxygen consumption is directly proportional to the amount of degradable organic matter and is expressed as the terms in dLT upon dt minus kLT, where LT in milligrams per liter is the oxygen equivalent of the organic remaining at the time t, and k in d inverse, that means days inverse, is degradation rate constant. K is degradation rate constant. L naught is the oxygen equivalent of organic matter at time t naught. And in the above context, the correct expression is, so first of all, what is BOD? What is BOD? So BOD is termed as biochemical oxygen demand. Biochemical oxygen demand. It is defined as the quantity of oxygen required for the oxidation of biodegradable organic matters. So the amount of oxygen, the quantity of oxygen that is going to be used in biodegradable organic matter, to reduce the biodegradable organic matter. So to oxidize, we can say for the oxidation of biodegradable organic matter, and it is done by aerobic biochemical action. It is done by aerobic, that means with presence of air, biochemical action. Aerobic biochemical action. And we have seen somewhat this kind of relation in last chapter, that was Check's law. For us, it is given that dLT upon dt is equal to minus kLT, right? This is given. What I can do from here is dLT upon LT is equal to minus k dt, right? And if I integrate both sides, this is from L0 to LT and this is from 0 to t, I get the value which is ln LT upon L0 equal to minus k t. So that gives us LT is equal to L0 e to the power minus k into t. And what is LT? See, what is L0? L0 is the biochemical oxygen, biodegradable organic matters which were present at time 0, means at the time when we started observing, and so it is at time when we are starting observation or at time 0 we also say that. LT is after time t, how much the amount of biochemical biodegradable organic compounds are still remaining. So LT is the still remaining amount. So, and we say that if we do, what is the difference between this L0 and LT? The difference between L0 and LT is what gives us biochemical oxygen demand. So the BOD remaining after time t is nothing but L0 minus LT, and which is L0 minus L0 e to the power minus KT, which is L0 1 minus e to the power minus KT. So the correct option is option B. Next is total Zeldal nitrogen concentration milligram per liter SN in domestic sewage is the sum of concentration of. So total Zeldal nitrogen, first of all we should see. For this we should know what is the significance of nitrogen in water. So the nitrogen in any water indicates that there was some kind of organic contamination. That means when water is contaminated by sewage, then nitrogen compounds are traced. Then we trace the nitrogen compounds in water and we can say, yep, there was something called sewage organic matter contamination. So we can trace the compounds which are, so the compounds we trace is ammonia nitrate. Compounds we trace is ammonia nitrate. Second, organic compound. Third, nitrite. And fourth, nitrates. Right? So these are the four compounds that we trace whenever there is organic contamination. Now, what is total Zeldal nitrogen? So for that we should know what is Zeldal nitrogen. So Zeldal nitrogen or total Zeldal nitrogen is nothing but this one, free ammonia. This is ammonia nitrogen. So free ammonia, that means ammonia nitrogen, and organic compounds, organic matter, organic compound, organic nitrogen we say. Compound also we should remove, we should write it as organic nitrogen. Ammonia nitrogen and organic nitrogen in total known as total Zeldal nitrogen. So the correct option is organic nitrogen and ammonia in sewage, option number C.